So this is the golden age of like experimenting on human beings, which is something I like to do. So it's kind of awesome. So if you want to now run an experiment on 100 million people, you can do that. You can get results back like in 3 days. So it's great. But the flip side is a lot of the inferential tools that we've had, mostly coming out of statistics for the last century, they don't scale to this level. And the vast amounts of data really help with some inferential problems, but they don't solve others. And people often get confused which problems just the large data helps with, which problems it doesn't, and what you can do about it. This project started in 2012 when a graduate student of mine, Erin Hartman, she was the head of all internal polling for the Obama campaign. And she needed to do a 10 million person experiment, and she needed to have like the adjustments done in the experiment right in the design, which meant that you're doing an experiment on 10 million people, but at the end of the day, you're not just going to be interested in the average effect of treatment minus control. And these were experiments on trying to get people to turn out to vote. What you're going to be interested in is what was the effect of women in Mississippi who are African American versus Hispanic males in Texas, so on and so forth. You're going to be interested in subgroups, which is a general problem, right? Because now when we have big data, the human mind wants to ask more from the data. So we want targeted heterogeneous treatment effects to people. So that's one thing. So she wanted to do it on the subgroups. The other thing was you're playing this complicated game that you wanted the analysis to be as transparent as possible because the policymaker needed to understand it. And the policymaker understands difference of means. The policymaker is not going to be so happy, even if you could get it to work, to say, all right, I'm going to like do this experiment on 10 million people, and then I'm going to run a support vector machine on top of it, and I'm going to plug out an answer for you. They're not going to be too happy about that, even if it did scale. Because you're in this adversarial game. Because a lot of the times what you're going to do is you're going to say a lot of things don't work, and the person that just got paid $20 million to run an ad campaign is not going to be happy that you just told the principal that didn't work. And that person is then going to try to do everything they can to undermine that result. So the transparency really kind of matters in that use case. So if that's your use case, statistics has had an answer to this for almost 100 years, which is you should block. Which you should compare men with men, women with women, Hispanic people with Hispanic people, so on and so forth. And within those cells, you can get cell level estimates. And then if you still care about the average across the whole population, you can take the average across those cells. We call those cells blocks. And that's called blocking, right? It's a very old idea. The thing about that idea of blocking is, in the general case, it's an NP-hard problem. So it just doesn't scale. In some special cases I'll talk about, there are polynomial time solutions to the NP-hard problem, but the polynomial time solutions actually aren't fast enough. Like n squared, the worst case about n squared plus other terms, n to the third plus other terms in computational complexity, space complexity is about n squared. Neither of those is sufficient to make it work at scale. Because the other thing about this 10 million person study was they're not going to give me the data to run it, and I can like parallelize it and do this and this. This has to be done on their computers because of the data confidentiality. So that's how this started, right? Tech firms also have this problem in spades now because you have these large experiments, you're interested in subgroups, and you need to know how to analyze them. What they and other people also have is not just the experimental part, you also have observational data, which I'm also going to talk about, and we're talking about estimators there, in which you didn't randomize, but in your data that you got, some people saw one ad and not another ad, or some people got one encouragement to get it to vote and not another one. You have a whole bunch of covariates on them, and you still want to say something, right? So maybe then you want to compare men with men, women with women, so forth, active daily users versus less active daily users, to say that, well, you know, conditioning on those covariates, those people are similar, and maybe I can make a causal-like estimate. And so that's not randomization, but that also is an NP-hard problem, and that's called matching. So I'm going to also talk about that. And the key things to understand here is that in these use cases now, with the data growing the rate they are, polynomial time's not good enough. And I'm going to focus for most of the talk, for about half the talk, I should say, about on the blocking case to build intuition. And then that's the same estimator that's used, the same algorithm that's used for matching and the clustering case. The back end is kind of the same, right? And Right. So the first thing to note is that just because you have a large data, it doesn't solve all your inferential problems. It's not like, oh, now things get simple. So say you have a randomized experiment. That seems to be like the more intuitive one about, hey, if I have a randomized experiment of 10 million people, or these internet firms, 100 million people, maybe I just take difference of means and I get an estimate of whether the ad worked or not. It doesn't work out that way. First of all, as I was saying, as human beings, now if you have so much data, it's not like you want to does the ad work on average. Does it work for specific people, right? Because we're in the world of actually targeting ads, even like on TV ads. So this election cycle, it's now in some areas. If you have DirecTV, you're going to get ads targeted exactly to your household. If you have Comcast, they're not, but in the next presidential election in Comcast, they will. In some cable places, like in Texas, you are getting ads targeted to your household. And they're optimized for your household based on your covariates, your voting history, because we yanked that from the voter file, census data down to your precinct, your imputed income, what magazines you subscribe to, your imputed credit history, so on and so forth. And they're targeted for your household. We're not exactly sure who in your household has it, but that's okay. And then once we know who in your household it is, we also target all your devices. Because if you use your smartphone, right, you probably use it at home and you're often, and then it's hooked to your Wi-Fi. And then I have a link between your Wi-Fi and that device, so I can now follow you to work, and I can target you there too, based on your household. Right, so that's like now these subgroups, and now the experiment's not so big anymore. And the second thing is when you have these like really, really large experiments, you're going to do this thing in the field, you're going to treat millions and millions of people, you start getting really interested in very small treatment effects. Right, because small treatment effects really matter because they get multiplied by a really, really, really big number. The core data science team at Facebook also had the slogan, which now needs to be updated, which I love, which is with great power comes small effect sizes, 1e to the -9. And now that they have more than 1 billion users, you know, they're going to make that number smaller, right? Which is to say that you might have very, very large data, but you're interested in very, very small treatment effects. So you need great amount of precision that just doesn't come from just having 100 million observations. One of the dirty little secrets of the whole ad industry, which is what supports most internet firms, is that if your outcome of interest isn't click-through, but your outcome of interest is, oh, does this ad actually generate revenue relative to the opportunity cost of using your money somewhere else? Most all experiments are too underpowered to give a significant result one way or another. And the reason for that is the median person doesn't click. The median person who clicks doesn't spend anything. So the interquartile range in the data is 0. Right? So you might have 100 million observations, but 80 to 90% of them are just zeros. Right? So you have this very fat-tailed process, and you don't actually have 100 million observations. So you don't have that much statistical power. And then the old way that we know well how to get statistical power is we do adjust on covariates. If we start comparing, active users with active users, non-active users, people who voted last time with other people who voted last time, so on and so forth, we're gaining statistical power. One way of intuitively thinking about it is if I have some data and I have an outcome and I have like the prior outcome, and if I regress the outcome on the prior outcome, if the R squared of that progression is say 0.8 and I adjust on that prior outcome, that's having 5 times the sample size. Right? So getting those, so instead of a 100 million observation experiment now, it's kind of the equivalent of having a 500 million observation experiment, which is more people than there are in the United States. So I can't actually do that, but I can get that kind of statistical power gain, right? The problem with that is now I gotta like find a way to adjust those covariates at scale. And this blocking, post-stratification matching thing we're gonna talk about does that. The other thing what's going on in practice is because these things are hard to do, these adjustments, because they're NP-hard problems, what people end up doing is like this famous public case of a Facebook experiment. It was an experiment done to get out the vote in 2012. And once they're done with matching all these databases, they have about 30 million people in the US, and they're trying to encourage them to vote. And the outcome is, was this Facebook encouragement to vote successful? They have 30 million observations, they run the data, and they get no significant treatment effect. They go, okay, that's kind of bad, because they just difference of means. Maybe we should condition on whether the people turned out last time, because that's going to reduce your variance. Because a pretty good predictor of whether you're going to vote this election is whether you vote in the last one and the one before that. Okay, so then they condition those two covariates, and now they get a significant result. And then they try to publish it. The problem is that if they had gotten a significant result to begin with, they wouldn't have adjusted for those covariates. right? So they've done this post-selection problem for which there's a growing literature in statistics. In psychology, they call this kind of behavior p-hacking. What basically happens is because your second hypothesis test was decided, you only decided to run it based on the results of your first one, your second hypothesis test is no longer valid. It needs to be adjusted for that you ran a first one, you didn't get a significant result, and that's why you ran another one by adjusting for covariance, right? So you can get lots of data and you still get 0 results, right? So it's like kind of a very interesting problem. There's another host of problems which is often called like randomization bias, in a sense that if I actually do an experiment and I flip a coin, it's easy to see this in medicine, that if I randomize a bunch of people to get some drug and the physician is forced to flip a coin, that's going to give you an unbiased estimate for that experimental sample if the physician was to flip a coin. In reality, physicians don't flip coins. Physicians in reality look at patients and patients look at physicians and they decide whether to take the drug or not. Right? So the people who are going to actually take the drug in practice might be quite different than the random sample that got it in your experiment. Right? And if you're a policymaker, if the health regulator, you actually don't care what the treatment effect is on a random half of the sample. What you care about is what's the random effect of the people who would actually get the drug in practice. Right? And now you have to start adjusting the experiment to get to that. Another version of this happens a lot in internet firms is that, okay, I'm going to change my ad auction. So I'm Bing, I'm Facebook, I'm Google, and I sell ads. That's how I make money. And my system is very complicated, and I want to I constantly do these little bit of experiments, right? So say I do a little bit of an experiment to change how I measure quality. The quality of the advertiser is a key function of the ad auction. So say change it a little bit, and I get a no result. And if I change it in my experiment, I usually do like on 1% of my sample, or 10%, or 1/10 of 1% of my sample, and I get a result. I have to be really foolish to think whatever result I get, that's the result I'm going to get if I roll out this as a policy change. And the reason is if I roll this out as a policy change, now Amazon's going to throw 100 engineers to game me. Right? Amazon's probably not even going to notice if it's 1% of their ads, I've changed how I evaluate how their pricing and how I'm deciding, or 1/10 of 1%. Once it's now a policy, now it's going to get gamed by some very smart engineers who are playing a non-cooperative game with me, right? So again, if I want to interpret that experiment, I got to plug it into a model that tries to model that strategic interaction. And if I don't, I make really, really bad decisions for some advertisers. Turns out most advertisers are really naive. They're not Amazon. They do really dumb things. But some, like Amazon, will eat your lunch if you do dumb things, right? So in observational studies, it's probably a little more intuitive, the problem. Just because you have lots and lots of data doesn't mean that any estimate that you have, you get to interpret to be causal, right? Just because I have lots and lots of data, that still doesn't mean the smokers are like non-smokers, right? It doesn't mean the people who see one ad are like people who see another ad. Right? So you got to do something to adjust for that. So the usual assumption that's going to have to be made in most of the literature is, okay, if I condition a bunch of covariates, right, men with men, women with women, so on and so forth, that conditional on those sets of covariates, treatment was as if random, right? And then I can sort of interpret the treatment effect as causal. Maybe that's true, maybe that's not, it's usually not, but that might be better than the unadjusted estimator. Now the thing about that is, well, there's nothing about sample size in an observational study. That means as my data set grows large, the people who get treatment, the people who get control become more similar, right? Just as n grows large. I got to do something. And in that case, it's like the matching version of this blocking statement, which is, oh, I got this data, and I want to match people with similar covariates together to make them similar, right? And this is another NP-hard problem, and this is like put in pipelines of various firms in really bad, cheap ways that don't quite work. So I'm going to talk about the experiment case first, and then I'm going to talk about the observational study case, and I'm going to briefly talk about the clustering case at the end. So just to jump ahead, I'm going to give you like the key results, and then I'm going to go try to give some intuition for how this thing works. Is that there's a new blocking, matching, clustering method, and it has like the following properties, which is that it minimizes the distance between every block, cluster, match group, right? And it's going to minimize the maximum pairwise distance. So I'll show it to you graphically in a couple slides. So you have a bunch of data points, right? And say you have 4 data points. It's going to compare, well, it's not going to do this, but one intuitive way of thinking about it is you compare all the pairwise distances between those 4 data points, and it's going to minimize the maximum pairwise distance. Call that maximum pairwise distance lambda, and it's trying to make that small, right? So it's going to make the infinity norm small, right, for the pairwise distances, right? And the method is valid for any distance metric that has to satisfy the triangle inequality. We use the triangle inequality a lot to get the theoretical results, so, but most things that people think about satisfy that. It ensures good covariate balanced design. So if I design an experiment based on this, right, it's going to really fast already make sure that between my treatment control groups, the covariates look pretty similar even before I do the randomization, right? Or say I run this algorithm after I've done the randomization, or like in the Facebook case, even with 35 million people, it turned out that there was just subtle little imbalances between who got the various treatments and their previous voting history. And if I do this to start grouping the data together to make it more homogeneous, it's going to do that, and they're going to gain statistical power, right? And unlike any other method, it works for any number of treatments and any minimum number of observations per block. This is the key thing. It's sort of like the only previously polynomial time, and polynomial time, as I said, is not enough. The only previously existing polynomial time algorithms only work for the case where you have 2 treatments. It's literally an A-B test. It's A versus B. But part of what's happened in this golden age of like experimenting people is people now run like 70 arms of experiments, and they might on top of it put on you know, a Bayesian experimental design to figure out which ones to weight up and which ones to weight down. So what you need is something that can handle more than 2 arms, A and B. The second thing to note here is that what you got to decide, the parameter you got to set in this problem for the algorithm is just the minimum block cluster match size. So take the clustering case. You don't tell it how many clusters you want, which from a statistical point of view is a very weird thing to do. It's like, I don't know how many clusters there are. If I'm going to cluster the data to try to get, like, say, an estimate, a treatment effect estimate for a subgroup of the data, I don't really intuitively know how many clusters I want. But I might know what's the minimum cluster size I want, right? Because the minimum cluster size is going to be enough for me to get an estimate in that area. So what this thing is tells, give me the minimum cluster size, give me the minimum block size, give me the minimum match size, and I'll do the rest, right? And what it's going to do is going to obey that minimum, and some of the groups might be a little larger than that because it's going to obey the natural clustering in the data. But it'll never result in any block cluster match group that's smaller than that minimum, right? So if this is like kind of key to the problem, right? If I have 5 treatment arms, I don't want groups of less than 5 because that's going to really complicate my experimental design, right? I might not even want groups less than, say, 10 or 20 because if I have 5 treatment arms and I group my data into blocks of 5, I can't estimate the variance within those blocks, right? And that might not be a great thing either. So I might say something like, oh, I have 5 treatments, I want a minimum of 20 observations per group. And that way I can get estimates within each of these blocks, and I can estimate variances within these blocks as well, right? So that's the thing. It's fast. It's n log n, expected time. I've taken out covariates here. It's n log n and number of observations. I'm going to talk about covariates later and how it scales with that. And the key thing about it actually is memory efficient. It's linear in storage. And that's what's the bottleneck that's actually killing most of these other algorithms, is the storage part. Yeah?
How does this depend on the dimension of the covariate?
I'm going to talk about that. And let me go. It's not as good on that, but that's not, I think, given the feature of the problem is adapted to this, not bad. It's inheriting whatever you inherit from the nearest neighbor graph algorithm you use, right? So I'll foreshadow it that way, right? So it's approximately optimal. It's be guaranteed in the general case to be 4 or less than 4 times lambda. So the maximum pairwise distance is lambda. This is guaranteed to give you an approximate result that's equal to or less than 4 times lambda, right? There's special cases, and they're really kind of important special cases. With one covariate, it's guaranteed to be lambda, which is almost a trivial algorithm. With 2 covariates, it's guaranteed to be 2 lambda. And as we're going to talk about later, you can prove that no polynomial time algorithm exists that is better than 2 lambda minus epsilon. This is a very important use case in a sense that I'm not really going to talk about estimation here, but this gets to Bin's question about covariates. When you're doing this matching and blocking and clustering for experimental design, it turns out the most important covariates you have are things you don't directly observe, but you can think about analytically, which is, oh, you need to know, if you could observe it, what the expected outcome is for any individual under treatment and the expected outcome for any individual under control, right? Call that Y0, your expected outcome under control, and Y1, your expected outcome under treated. And that's actually what you want to match, block, or cluster on, those two covariates. And all the other X covariates you have, all the other features you have are just being used as proxies for those two, right? So a very important use case in production here is I use other data to estimate maybe prior data, and I estimate my outcome based on a whole bunch of X's, and I try to get an estimate of Y0 and Y1, right? What often is done in practice, I tell people to do is estimate, because they usually don't have like the data in treatment, they usually have the data in control, they usually have like lots of it. You estimate Y and X, I don't care how you do it, use your favorite machine learning algorithm. You get a Y hat, your predicted Y for every individual in the experiment, you match on that and the prior outcome, right? And call it a day. And that's like the feature selection kind of step. Because analytically, all you need is Y0 and Y1. Your predicted outcome under treat and control, that's where all your variance gains are coming from. That's where everything's coming from. All the other X covariates are just being used as proxies for that. And I'm going to talk about this a little later. As the dimensionality of X grows large, if you start using it all, you actually get yourself in a world of problems. It's very similar to k-nearest neighbors that a lot of people here might have intuition with. As if I do k-nearest neighbors and the dimensionality is growing large, I'm not getting good. So I got to do a feature selection step is like kind of like key. Anyways, right, but I'll talk about that more in a sec. So in a few slides. So there's current blocking approaches that I'll just talk about briefly. So the only case that we have a really good practical algorithm for is the case of just those two treatments, just A and B, right? In the A and B case, it is a polynomial time problem. And there are polynomial time algorithms. It's a network flow problem, for those who know the CS literature. And it's like those kind of algorithms can be used for this, right? And that's called like pair matching, which is, no, those are restricted to like everything that you pair has to be like just observations of two. So I'm creating clusters of exactly size 2, right? And those algorithms can be used like before I randomize. So in the blocking case, and then I'm going to flip a coin, one coin within each pair. Right? And that's going to define whether the first one is heads or tails and the other one gets the opposite, right? So this works okay if it's, if you have enough data. I mean, if the data is not too large because it's like n to the third plus other terms, if you have A and B, just two experimental conditions. It doesn't work well if you have more than that. It also doesn't work well even if you have two experimental conditions. If I just want to make an inference to those like blocks, then I gotta have to start matching blocks to blocks, and now I'm back in this computational problem. As I'm going to show you, what part of the other problem is, it breaks the natural clustering in the data, right? And I'll show you examples of that in a sense that because each of the blocks has to be paired, right? It's going to break, if there's some natural clustering in the data that should be obeyed, it breaks that. Statistically, it can't estimate like conditional variances for the reason that I can't estimate the variances within a block, right? Because I have, two treatments, I have two observations, right? And then I have difficulty, how do I work with that? I have to start averaging over blocks and posing smoothness assumptions and all these things I don't actually have to do if I didn't set it up that way, right? So to our knowledge, we're the first ones, like for this blocking, matching, causal inference kind of thing, to propose like a completely different way of thinking about the blocking problem. All the other proposal literatures have fixed size blocking or fixed size clustering, right? And ours is like threshold blocking, which is a lot more like has a feel of much more like clustering. Because all the previous algorithms are like, well, you pick the exact size, and the exact size is usually 2, because that's the one that you have polynomial time provable solutions to. So you group the data into pairs, right? And now, of course, there's a cooked up example to make it look not so good. With threshold blocking, you just set the minimum block size. In this case, the minimum is 2. But if there's natural clustering in the data, it's going to cluster more than just 2. Right? So if this is x1 and that's x2, and these are the two covariates you need to block on, fixed size blocking is going to pick some not so great blocks. The one right here, for example. Right? And threshold blocking is going to group the data naturally. Right? Because it has this thing that it's going to obey the minimum, but it's going to allow to obey the clustering in the data. Now, Now, whether this is threshold blocking is better than fixed size blocking, if, you know, at the end of the day, you're using this to estimate something, gets into this delicate issue that I'm not really getting to this talk of how this x1 and x2 relates to your outcomes, right? Say what you do is you find two covariates you want to block on or two covariates you want to match on, and they turn out that you were wrong and they have nothing to do with the outcome. It turns out you were better off doing the fixed size blocking than the threshold blocking. And the reason is if you have just two treatments, A and B, this one is maintaining equal probability treatment assignments, 0.5, right? And the x covariates are just noise. This one isn't, because that's 0.5, but that one isn't, and that one isn't, and that's adding a little bit of extra noise, right? But if those x1 and x2 are related to your outcome, which I hope they are, that's why you're doing this, right? Then this is going to be better because it's going to minimize the gap, right? And this is part of like intuitively why you want the x's to be the things that predict y. Because if they're not, you know, it's not clear why you're doing this, and you might be better off actually not doing it at all, right? But that's the intuition for what's going on, right? You can prove that if you're interested in minimizing the distances in, like, say, x1 and x2 by any distance metric that satisfies the triangle equality, that threshold blocking for any objective function for any desired block size will minimize that objective function better than fixed size blocking. And that's pretty intuitive because the threshold blocking search space is a superset of the fixed blocking search space, right? So it can't be worse. So it's gonna be weakly dominant. But that comes at a cost. The cost it comes at is like twofold. Well, the first one is true of all blocking, that the objective function that you're minimizing, in this case, I want to minimize the distance in x1 and x2 covariates, might not be the objective function that you actually care about at the end. And the objective function you care about at the end, as I said, it should be the distance not in x space, the feature space, but in the space you don't directly observe, which is y0 and y1. Your outcomes under treatment, your outcomes under control. Right? The second one is, even in the case of two treatments, the threshold blocking problem is an NP-hard problem, which we prove, which the fixed size blocking problem is not an NP-hard problem. That is a polynomial time problem. I'm not going to give you the reduction here. You can intuitively see it in that slide, right? But it works. It's like fast. So I'm going to give you like the results for like how it scales, then I'm going to try to walk you through the algorithm and give you some intuition. So here's the I gave you the analytics for it. Here's the some simulations on data. It's based on like some actual data. So it scales like n log n, and it actually does scale n log n. This is like a really simple, run on one chip, desktop CPU, 100 million, you know, our algorithm, these are two. The blue line is our algorithm with some heuristic improvements. The heuristic improvements make the block sizes small. And the red line is just the algorithm as just like the one that's going to give you the approximate 4 lambda bound. It scale, you can tell they're scaling pretty n log n quasi-linearly. And these are the other algorithms which just explode and they're not, you know, they don't even, you know, I just give up on these. And it turns out with these algorithms, even like large internet firms end up not having grave difficulty applying them in pipelines with like 150 million observations, and it's not for a lack of engineering talent. It's just, you know, it's just like they're exploding. So it scales really well in practice. I mean, it's kind of jarring, right? Because like it will scale like it will block like 100 million observations in about 15 minutes, which is what the usual algorithms do for like 10,000 observations, right? So. Yeah, and the key thing is the memory usage is linear and complexity, and that's what's giving it to you. And I'm going to get to the covariate space in a bit. So here's the intuition for the algorithm. The key move here was we're actually not solving the optimization problem as stated. We're solving another problem, right? And we proved that solving this other problem actually proves the problem we care about, right? Although it might not be totally obvious that it does. But this other problem you can solve because we're leveraging off a lot of the work done on fast algorithms for creating nearest neighbor graphs. So we're not actually directly optimizing the objective function. We solve another problem, and then the whole proof thing is to prove it bounds and solves the problem we care about. So here's an example. And the first move is to think about like these blocking, matching, clustering things as a graph theory problem. So every point here is a data point, and consider two covariates, x and y, and every point's a data point. And these are all units. I think there's 12 here. And say we want a minimum block size of 2, right? So the first thing to do would be is to say, oh, if I want to like minimize the pairwise distance, I'm going to like take the distance between every data point and every other data point and try to figure that out. Well, I don't want to do this because that's an NP-hard problem now. So that's not good. I can't do that. I can't brute force. That's the brute force thing, and that's not going to be clever. So I'm not going to do that. It turns out what you can do is, okay, I'm going to start by creating the k-1 nearest neighbor graph, and k, remember, is the minimum block size, right? So it's the k-1 nearest neighbor graph for those 12 points. Okay, that's fast. I can do that, right? So then I construct the second power of the nearest neighbor graph that I just constructed. All right, that's still fast, right? And then I find a maximal independent set and seeds. And these seeds don't have to be smartly chosen, right? This is why I can do this fast, right? I just need to find seeds whose neighbors are not neighbors of any other seed, right? If I assume that I did this optimally, then I could hit lambda. Of course, if I could do that optimally, finding those seeds optimally is an NP-hard problem. So you don't assume that. You just assume that you can find some seeds whose neighbors are not neighbors of any other seed. That you can do very quickly, right? And that's not an NP-hard problem, right? And then what you do is from these seeds you found, you start growing out the foreign blocks, right? You find the first thing you do is that all the neighbors of those seeds are blocks, and then you block them off, right? And at this stage, for some use cases, you'll just stop the algorithm. At this stage, by the triangle inequality, you can prove that the maximum distance, pairwise distance between any of the points is 2 lambda, right? Because you can just see it here, right? Because the maximum distance between any seed and its neighbor is going to be lambda, right? And then the distance between any other 2 points, any blocking is then going to be 2 lambda, right? But then I might have some data points that are unmatched, right? So a lot of use cases, someone says, oh, I want to do an experiment. I'm going to take it off the voter file. I'm going to take 50 million people, and they don't actually really care to do the experiment with the 50 million people. They just need some number. You can run it and stop the algorithm here, and then you get a 2 lambda result, right? But then you can assign the remaining blocks to the nearest block centers, and that's what's giving you the 4 lambda jump now, right? And that's sort of like the intuition for how the algorithm goes and the intuition of the sketch of the kind of the proof. The hard part is to prove that that actually solves the problem we set out to solve. And the second hard part is going to be to prove a local optimality property. So unless p equals np, there is no polynomial time 2 lambda minus epsilon proximate algorithm. In the general case, ours is, remember, only 4 lambda. So there might be a better one, although I don't quite see it. We proved that the algorithm I just sketched out provides a valid blocking. The algorithm I noted is working on the undirected graph. In practice, it's slightly better in practice to use the directed graph. You can't prove that it works better, and it's a little less intuitive to explain to you, so I didn't explain to you the directed one. It's proximally optimal. And the other key and kind of cool result that wasn't obvious is that you have a local optimality property, which is that for any subset of blocks from the blocks constructed by the algorithm, it's also going to be approximately optimal, right? So not only is it going to be a global approximately optimality result across your 100 million observations, it's going to be approximately optimal in each subgroup of the data, which is kind of key because part of the whole business of this was I want to estimate stuff in the subgroup of the data. And so that's like kind of nice, right? So I'm going to summarize this part of the talk. And one thing to know is it's closer to clustering than some other traditional designs, although it's not like, k-means or something. And then we proved the key property indirectly. We're not actually writing down an objective function then optimizing it. That doesn't work. You prove something else, then you go back to proving that this, which is basically the bottleneck graph problem, subgraph problem, solves the problem we care about. The algorithm's fast. So the key thing is, now I'm going to expand about covariates, is that you do the nearest neighbor graph construction. And net of however you've done the nearest neighbor graph, its computational complexity here, k, now is the number of covariates. Ignore d for a second. It's kn time and kn space. So net of the creating the nearest neighbor graph, it's linear. Right? Now, so in both covariates and n. Now, because the nearest neighbor graph is sort of incorporated all the covariate information. Now, the problem is nearest neighbor graphs are not, don't scale great in K-space, right? So if you do KD trees, for example, right? So then it's 2D kn log n expected time, 2D kn squared worst time, and kn. And then, I'm sorry, I shouldn't have said ignore D. So D is the covariates, K is the minimum block size. I screwed that up. So K is like, if I say, oh, I want minimum block size of 2. So think of that as the number of treatment arms. D is the number of covariates, right? So once you have the nearest neighbor graph, the number of covariates doesn't enter into it anymore. But the number of covariates in the nearest neighbor graph is a real problem. For KD trees, it's 2D, for example, right? So that's going to like really kill you. So now you can have like approximate nearest neighbor graphs, right? So, I don't have to do KD trees. I can like get an approximate algorithm, and that's going to scale a little better. But I don't think that's like a great idea, because the underlying problem here is as x grows large, you actually, even if you could get the optimal solution and you have an x of say 1,000 dimensional space, you don't want that 1,000 dimensional space, right? A lot of it in this data is pretty sparse. A lot of those x's actually aren't very powerfully related to the outcome net of other x's, right? So you really want a pre-processing dimension reduction step. In these large data cases, that's a very natural one arises because you have lots of prior data usually to try to estimate y as a function of x and then match on that function of y, plus maybe one of the few leading x's, right? I've yet to find a use case that you can't like just match on like the prior x, maybe the first principal component and some estimate of y and just call it a day. There are some use cases like say the ad optimization one that you care about every 1% gain. But usually you'd rather have the simplicity of the pipeline and forego a 1% gain. It's like the Netflix challenge. They actually never implemented the algorithm, right? They implemented only 2 parts. First one was like the fancy thing called factor analysis, because I gave you like 80% of the gain. And that one you can actually put in a pipeline. Right, so that's how it scales there. So this, either way, it's way better than in terms of n than the network flow algorithms, which only work, which don't scale enough to work, right? So in observational data, I was saying that you have similar problems, and now here it's like much more delicate to work with in the sense that in an experiment, the experiment is asymptotically valid, and you want to juice up its power in finite samples, and I was saying even 100 million is finite samples, given the oddities of the data, the fat tails of the data, subgroups, after small effects, sizes. In observational data, you don't have any of those guarantees that as the data set, whether people who take treatment are very different from people who take control, right? It's just not a function of like data size, right? I mean, it could just be, as your data goes large, you're just getting a more and more precise estimate of a very biased quantity, right? But people might want to then in that data compare apples to apples, oranges to oranges, so on and so forth. In this big data world, I don't mind it less because you can do these observational data studies and then you can go do an experiment to see if your observational method worked, right? And then you can like validate it in a particular way. So we apply the same thing to this problem, and it turns out that the same in the case of 2 treatments, just A and B, there is a polynomial time optimal algorithm that exists, which is parallel to the one in the blocking case, because it looks very similar. I'm going to just jump to that. And ours is a generalization of that, right? So the previous algorithm, which works for like just 2 treatment conditions, it's called full matching, right? It satisfies the constraints that each unit must be assigned to a matched group, right? And each group must contain at least 1 treated and 1 control unit, and then you're going to within that matched group estimate a treatment effect. Right? So we generalize that to say you have K treatment conditions, right? And each unit must be assigned to a matched group. And each group must contain at least TI units for each treatment. So we're way more flexible, right? And each group must contain at least TAA units in total, right? So you can it's set in this group, how many treatment units you want in the group, how many total units you want in the group. And so, if you have 5 treatments, this will work. If you have 5 treatments and you want 10 treated units and 20 data points overall, it'll satisfy that. All the usual methods won't. Although this one is exactly optimal and we're only approximately optimal. It's not a small difference, right? So one way of thinking about like this problem in general is like in the matching problem, you have like 3 things you got to do. You want to construct match groups that are similar to each other. You got to define what similar means, and that's the objective function, which I'm not going to talk about, which is a real, and that gets back to the y1, y0 issue, because again, the objective function that you care about is that, and you don't directly observe those. Then you have like constraints about how do you want to, those groups look. Oh, I want at least 1 treated unit, at least 1 control unit. I want at least 10 observations, right? And once you've define those, and there's big issues with those, the properties of your statistical estimator are going to really depend on that, right? And we haven't really talked about that. Oh, okay, now we have an algorithm to construct that. I'm just talking about like this part. Just want to emphasize that. So to give like an intuition of what happens here, and this intuition I'm talking about in the matching case, but this is related to the clustering case, is that so I have a bunch of data points, and then say the red were treated and the whites were control. And this could be like an experiment that you've done that you didn't block on, because in the internet world you don't have blocking given that the way that the pipelines go. Or it could be observational data and people just took treatment and control differently, right? And the simplest algorithm that people usually use is nearest neighbor matching without replacement, right? So it basically says, oh, for every treatment and control, find me a nearest neighbor, and I'm not going to allow replacement, and the things that are not matched, I'm just going to drop, right? So it's not going to have great properties because this looks good. This one up here, these two up, well, my pointer is dead, I think. This one, if I use both pointers, maybe that will light up. These two look good, but this one's really bad. All right, it's like a very big distance, right? Full matching, which is the special case of ours, is going to like do the right thing in this case. It's going to cluster the data, so this will becomes a group. You have a minimum 1 treated, 1 control, and now these are pretty similar, this is pretty similar, and that's pretty similar, right? So that's good, and you don't really sort of like want to do that. And matching, and the thing about it, I'll say at this point, this matching without replacement, which seems like the simplest algorithm, is computationally slower than our algorithm. So like the simplest, most heuristic thing you can do that has no provable properties because you end up with this really bad matches is actually a slower computational algorithm than ours, which is kind of funny. Right? So one way of thinking about it is these big gaps here in this algorithm, that's introducing bias because those data points look very different. The data points that you've dropped are going to increase your variance because you had all these control observations that you could have used around here, but you just dropped them, and so now you're increasing variance, right? Full matching works great, but it doesn't scale, right? So it's still loading. It's not actually loading. It's a bit of a joke, right? Another way to build intuition in these things is that, if you have like data and you're like trying to do, and I'm going to do this in the matching thing, but again, the similar things are going on in the clustering and the blocking thing. You have a bunch of different like choices at a high level of how you want to group the data, right? And then there's matching without replacement, right? Which is like these the same figures before, just turned on its side, so it's easier to show you a whole bunch, right? And red are treatment, white are control, and it's going to match these things as close as it can, and then it's going to delete the rest. So you're going to like increase your variance, right? Now you have matching with replacement, and this is the fastest algorithm. What this is, I'm going to match a treated to someone in control, and I'm going to keep doing that. But if I already matched you to control before, I get to use you again, right? And it also, so this is fast. This is the fastest algorithm because it doesn't have to take track of anything. It just has to find the nearest neighbor, and then it's done. Right? It doesn't matter if the nearest neighbor's been used before. It doesn't care. But it does have the feature that it still drops a whole bunch of data, right? And usually what ends up happening in these applications is you have like lots of controls. You don't usually have as many treated, right? But if you have like, 200 million controls and you have 10 million treated, you want to use all those 200 million controls to reduce your variance. But it doesn't do that. And that one's the only one that's faster. You can have like K, 1 to K matching. It's just, oh, no, not just do 1 to 1, but I'll do 1 to 2. It's going to look like this in this data, and you have these very large groups. And then you have like full matching or generalization that it's going to always obey the clustering in the data and use all the data, right, to look like that, right? And you sort of want to and you want that done here. And it's not like there was any disagreement that this is sort of like the thing to do. It's just that it doesn't, even in the case of treatment control, even with the case of like 10,000 observations, it just doesn't scale very well, so people didn't really do it. So here's the scaling of our algorithm relative to the fully optimal algorithm. In the only case it works, which is you only have 2 treatments, right? We scale a lot faster, right? Because this is n log n. That one's not. This is CPU time. That's memory. And of course, the other algorithm does not work if you have more than 2 treatments, or if you have other constraints like, oh, I want at least 3 treatments in a block. I want block sizes of 20 or match sizes of 20 or what have you, right? So then there's like the clustering approach, which is this parallel to the matching and blocking. And I will say, again, the clustering thing is there's a lot of times I see like k-means, for example, being used for clustering in like a statistical context for effect estimation where it doesn't make a whole lot of sense to me. It's a heuristic algorithm, and they have to start picking like how many clusters you have, which no one has a great deal of intuition about, as opposed to, oh, if I'm going to cluster the data in a region and then I'm going to estimate something, way more natural ways to say is I want a minimum size, right, to get enough estimates there. And if you turn it to that problem, I can give you a provable approximate algorithm for that. Right? The other thing is being, and this is actually the competition just started yesterday, is to say you can do this as a dimension reduction step to go run a more computationally intensive ML algorithms. One way of thinking about this clustering matching is a way of discretizing the data or grouping the data without having you to pick cut points in the data. Right? If I apply the clustering algorithm to data, right, and then for every cluster, right, I'm going to say for every cluster, I'm going to like maintain summary statistics of it, like the mean of that cluster or the variance of that cluster, right? Maybe then on top of that, I can run a random forest. Computation of that started yesterday, right? So if I save 100 million observations, a random forest, and that's kind of hard, maybe I want to turn it into like, say, 100,000 clusters, right? And each cluster is going to maintain like the means of the cluster and maybe other summary statistics like the variance, and I'm going to run a random forest on that. And maybe that will scale, right? And then let it go. And the other thing I can then start playing with is, oh, when I do this clustering, I only use like major X covariates, major features, right? And once I've done the reduction to clusters, whatever estimator I use now there, I use all of my X's now, right? Because I use this thing to get the grouping on the major ones, and now I want that last little bit of extra information. And also once I've gotten local estimates, I can do things really fast locally. I'm going to use the whole X space there, right? So there's all these fun games you can like start doing with this thing, right? So to summarize, so a lot of these existing methods don't work well on large samples, and like it's like a little weird, right? In the sense that it's like on the one hand, like there's these methods that you just could never do before for experimental design. Now I've done it. You could write about them, but no one ever do them. Like these multi-arm bandit Bayesian experiments, now you can at scale. And then there's these very old traditional things like this blocking thing that actually don't scale. You don't do an internet scale, which is like an interesting world. We live in there's a lot of details for why one is much easier to scale than the other. So what ends up doing is applied users hack a lot of heuristic algorithms that don't have provable properties. And they usually have like worse computational efficiency than the algorithm I just proposed, because it's like really, really fast, right? In the sense that the only thing better than it is like nearest neighbor matching with replacement. If you have without replacement, i.e. once someone's been matched, I can't use it again, that algorithm itself is slower than the one I just presented. And that one's about as fast as you're going to get, right? And then the heuristic stuff people do, because there's often not a great deal of care taken, blows it up. Even in our case, when we have our algorithm, we have these heuristic refinements to make the clusters smaller, right? Because for some estimation things, even if the X's are not great predictors of the outcome, smaller block sizes are better. We have to be really careful, because a lot of the obvious heuristic things you think about, even though they're provable only polynomial time, the order is higher than an underlying algorithm. So you like blow up all the gains you have fought for. And in this talk, I've ignored estimation issues mostly, and they get like pretty delicate and interesting. And those things are not like, at least I would have thought you'd have to think about, right? If you have 100 million observations and 80% of your data are zeros, right? And even if you like log the data, there's still a fat tail sitting there. That has like very interesting things about it. From a pure statistical theory point of view, you've had these really things that like lots of different ways for us to, like, say, get variance estimates, right? And some of them are like based on asymptotic theory, and other ones are based on like permutation inference, going back to Fisher, or randomization inference that some of you may know about. And those are like give you exact values. Asymptotically, under pretty weak conditions, both of them should converge pretty nicely. So once you're dealing with sample sizes of 50 million or 100 million, you would have thought that they would have, but they don't. In a lot of data cases, and a lot of what's going on is, yes, you have 50 or 100 million observations, but the data is not well behaved, right? The conditions in which they converge at are weak, but they are still there, right? You have finite fourth moments and stuff. And the data seems to have finite fourth moments, but there's a constant term in front, right? And we have no intuition of that constant term. It seems to be that constant term is big enough that it's not kicking in, that to the point that even with 50 million, 100 million, you have enough difference. The last thing I'll leave off on about is that if you have these ad experiments, right, and on the one hand, someone goes, I'm going to do a difference in means test on them, and I'm going to do a variance estimate of that using usual textbook formulas, right? That is not in a lot of data cases giving you the same p-value as what I do is, oh, I'm going to do the permutation for sharing inference. The permutation for sharing inference offers giving you a much, much smaller p-value. Now, they're not testing the same null, right? One of them saying that the treatment effect of the ad is on average 0. The other one's testing the treatment effect of the ad is 0 for every individual, right? And those are subtly different, right? And then the other one's effectively putting in like a model of the treatment effect, while the difference in means one that you're all know and familiar with is not. But usually they're shooting off very differently. The thing that's a little scary is if you have 100 million observations, you see them going off into a very different spot. If you subsample the data down to, say, 1,000 observations or 2,000 observations, the size that we're used to dealing with, where a lot of literature is written about comparing the two, they look very similar, right? The confidence intervals overlap a lot. So you think, oh, they must asymptotically be headed to the same spot. And as n goes to 100 million, no, they're not. I never look at these tests the same way ever again. Anyway, so I'll stop there.